Today we're going to continue talking about electrostatics by talking about electric potential. It's energy. So we're going to move from the electric field into electric potential. So first and simple, we're going to determine the electric potential near one or more point charges. Then we're going to calculate the work done on a charge or use the conservation of energy to determine the speed of a charge that moves through a specified potential difference, which comes down with some of this. We're going to save these for our next discussion, 3, 4, and 5, and we'll talk about the relationship between pictures, representations of the electric field and electric potential. So we're going to hold off on that. Today we're going to calculate the potential energy of a system, the potential energy of a system and the work required to put that system together. Then we're going to work on integrating electric potential from the electric field. And then we'll talk about the general relationship between everything. So, that being said, let's get into it. So, we're going to start by talking about electric potential energy. What we need to remember is that potential energy is the work done against a conservative force. And just like gravity, we're going to say that's from infinity to the location that we're talking about. So to make that clear, let's pretend that we have a positive charge right here. And if we want the potential energy of a system of this positive charge and a smaller positive charge, what we're going to have to do is to look at the work required to bring that smaller charge all the way from infinity all the way to its location, R. So what we're going to do is use our relationship between potential energy and force. Okay. Because we know that our force will be changing that entire time. We're going to integrate that from infinity to our position, from here all the way into here, because that's how we determine the work done. That's how we determine the electric potential energy. It's the work done by me and the opposite work of the field. It's the force from the field. That's why we have that negative sign there. So if we plug in Coulomb's law, the force between those two charges, because this is electric potential energy, we take the integral of that. To show a few more steps with that, we'll pull out the K and the Q's because they're not being integrated. And so what we see is that we are integrating r to the negative 2 with respect to r. And so that gives me negative K Q Q times, well, that's, add 1, negative r from infinity being my initial location to r being my final location. So r minus r to the negative 1 minus infinity to the negative 1. Well, infinity to the negative 1 is 0. And this is what we get. Okay? So for us, the electric potential energy is going to be KQQ over R. And electric potential energy is a much, much nicer quantity to work with than force, primarily because energy is a scalar. So let's look at problems that are associated with this. Essentially, let's say we have, each time we see a Q, it's going to mean 3 nanocoulombs. So I have 1, 2, 3 charges. Each one of them is plus Q. And the question would ask something like, what is the energy required or the work required to assemble these charges, to bring them together from infinity? And what we're going to have to do is look at the potential energy between this charge and this charge, and the potential energy between this charge and this charge. Okay? Because when I bring, let's say this charge was here to begin with. When I bring this charge in, it does work against this charge, and it does work against this charge, and this charge does work against this charge, bringing it all in. They're all working against each other. So the total energy here, the total work required to assemble, would be electrostatic potential energy 1 plus electrostatic potential energy 2 plus electrostatic potential energy 3. This is 1, 2, and 3. Now, sorry, 1, 2, and 3. Now, if each of these is 1 meter apart, that's K times Q over R plus K times Q over R plus K times Q over R. So what we would have is 3kq squared over R. And you could plug in the numbers if you wanted to, but it's just additive. It's completely additive. And it's all positive energy. That did absolutely nothing. Likewise, if I have a positive charge here and a positive charge here, and I bring in a negative charge Q from infinity, the electrostatic potential energy of this system, to bring them all together, is the electrostatic potential energy between these two, the electrostatic potential energy between these two, and the electrostatic potential energy between those two. There are 3 different interactions that we have to deal with. So our total energy for this system, or total energy stored in this system, is 1, 2, 3. K times Q over R plus K times Q times negative Q over R plus K times Q times, again, negative Q over R. What we're implying here is that because this is a negative charge, there is negative energy between these two, negative potential energy. It's just like bringing 2 masses that are attracted to each other together have negative total energy. These two are going to have negative energy from being stored up together. We're going to do a lot of problems like this. The next thing that we have is electric potential. So, before we had force, and that was what, KQQ over R squared. And we looked at that in terms of the electric field, which was the force over the charge, and that gave us KQ over R squared. Well, likewise, we have electrostatic potential energy, that's KQQ over R, and we're going to look at it in terms of electrostatic potential energy per unit charge. So instead of looking at the electrostatic potential energy between 2 charges, we're looking at energy per unit charge in space because of the charges around it. We call this potential difference or voltage, and that's just KQ over R. So it goes by potential, goes by voltage, goes by potential difference, it goes by electrostatic potential difference, it goes by electric potential. It has a lot of names. Mostly, we just don't call it energy. If it says potential and doesn't have energy behind it, this is the thing that we're talking about. And this, again, is a whole lot easier to deal with than the electric field, because the electric field is a vector, and direction is important, and it can cancel itself out. Potential, on the other hand, isn't a vector. It can't cancel itself out. In fact, looking at it, let's erase it so that we can see what we're looking at. Looking at it, electric potential difference being KQ over r, this being the distance I am away from my charge, q, if q is positive, V is positive. So I get positive voltage from positive charge. But if Q is negative, then voltage also will be negative. I get negative voltage from negative charge. That's the only place I can get negative voltage is negative charge. And the only place I can get positive voltage is positive charge. Looking at this, I want to try to find the voltage at A, B, and C, which is 3, 0, due to these three charges. This one's positive due to these two charges. This one's negative. So the voltage at A is going to be the voltage from charge 1 plus the voltage from charge 2. So the voltage from charge 1 is K times Q1, positive 2 nanocoulombs, divided by 1 meter. Not squared because it's voltage. It's a whole different formula. That's KQ over R. Plus K times negative 2 nanocoulombs divided by 1 to 3 meters. 9 times 10 to the 9th times 2 times 10 to the negative 9th divided by 1 is 18 joules per coulomb, plus 18 divided by 3 is 6. Negative 6 joules per coulomb, leaving me with a voltage at A of 12 joules per coulomb from both of those charges. Meaning overall, I had to do positive work in bringing any charge to this location. It does not look like a J. I did positive work in bringing any charge to this location. If I were to bring in a 1 coulomb charge from infinity to point A, it would take 12 joules to do that. 12 joules worth of work to do that. That's what that's saying. Let's look at B now. Point B is 1 meter away from each of those charges. The voltage at B is going to be, again, voltage from charge 1 plus voltage from charge 2. So that's K times positive 2 nanocoulombs divided by 1 meter plus K times negative 2 nanocoulombs divided by 1 meter. That gives me a voltage of B, they're identical except for the sign, of 0 joules per coulomb. That means that any charge that I bring there, 1 coulomb, 1,000 coulombs, I do positive work against this one, negative work against this one, and they cancel each other out. Meaning that it takes no work to bring any charge to this point from infinity. And then, let's erase that. We're going to look at our final point over here at C. The voltage at C is going to be V1 plus V2. K times positive 2 nanocoulombs divided by, now we're 3 meters away, plus K times negative 2 nanocoulombs divided by 3 meters away. That gives me a voltage at C of 18 divided by 3, 16, 6, joules per coulomb plus, and that's not 3 meters away, that's 1 meter away, plus negative 18 joules per coulomb, leaving me with negative 12 joules per coulomb at this point. Negative 12 joules per coulomb. Meaning if I bring any charge in here, any positive charge in here, I'm going to have to keep it from being attracted to it. So I'm doing negative work. I'm pushing against my displacement. And all of this has to do not with the direction that everything's pushing, but what kind of charge we're close to. Having to do with the work. Now, as a bit of shorthand, instead of writing joules per coulomb the whole time, we had a man named Emil Volta who so generously donated his name. So we're going to say that 1 joule per coulomb is equal to a volt. That's how we're going to define it. That brings us to accelerating voltage. And what that means is that we're going to take something that's at a potential of 0 volts to a potential of, let's say, 10 volts. And as that charge moves from there to there, let's say it's through a distance of 5 meters, we can find its velocity afterwards. Now, first question we have to ask is what kind of charge is going to want to go from here to here? If I put a positive charge here, it doesn't want to go towards more positive voltage. That means I have more positive charge here. So we'll be accelerating a negative charge through this voltage. So we have a charge of Q that we're going to move through this voltage. Now, we know that voltage is equal to KQ over R, but we don't know the charges that's giving us this, so we can't use that. We do also know that voltage is equal to energy, U, over a unique charge. And that's what's going to happen here. My change in voltage is going to be my change in potential energy divided by that charge. Or the change in potential energy is going to be Q times my change in voltage. Well, I know that my change in potential energy is also equal to the opposite, my kinetic energy. So 1/2 the mass of my charge times the velocity of my charge squared, negative, is equal to the amount of charge I have times the final voltage minus the initial voltage. That's going to tell me the velocity that this object has as it's leaving here. Because it's a negative charge, the negative signs go away. But this is going to help me find out how fast this thing is going as it shoots out. As I move through a change in voltage, it's going to tell me a speed. This is an example that we saw in class yesterday. And we did this example to find the electric field at this point. Well, we can also find the electric potential at this point. So the electric potential at Q is going to be the potential from charge 1 plus potential from charge 2. Well, that's KQ over A plus KQ over A. The voltage at that point is equal to 2KQ over A. That is so much nicer than having to find the electric field because there are no vectors. Also, the electric field was 0 there. Now, the question that we couldn't do yesterday was, if I have a tiny positive charge there, I have a tiny positive charge Q here, and I displace it a little bit, it's going to shoot away. It's going to accelerate away very quickly. And I want an expression for the speed that it's going to have once it's a very, very, very far distance away from here. In order to find its speed, we have to look at our energy. At this point, our total energy is all potential energy. And then when we are an infinite distance away, my total energy is all kinetic energy. 1/2 mv squared. I don't have any more electric potential energy. So I need to find out what my positive charge Q has as potential energy right here. And again, from voltage is U over particular unit charge, I know that my potential energy at this point is going to be that charge Q times my voltage. So my total energy at this point is equal to Q times 2KQ over A. which means that if I want my velocity, since I know the total energy here is equal to total energy at infinity, it's going to be equal to 1/2 mv squared. So I can just solve for that velocity. Now, it's not a particularly lovely number, but 4kq over m square rooted, and that's going to give me the velocity once I've accelerated the distance away. This is how we're going to use potential. It's a way of talking about energy without talking about a specific charge.